Hello math friends, this is AP Calculus section 3.4 day 2 notes. We're going to continue talking about the derivatives of our trig functions today. There are 6 derivatives up in the box. Hopefully you've made your flashcards and you've started working on memorizing them. Notice that our friend the unit circle is also back. Today we're going to be continuing to work on derivatives of trig functions, but we're going to be doing some application problems where we're going to have to evaluate certain functions at certain locations around the unit circle. So the unit circle is just there as a reminder in case you don't remember what cosine of pi over 3 is or what sine of 5 pi over 6 is, those kind of things. But if you don't remember your unit circle, hint, hint, start working on that as well. 2 other important definitions that are proved in the text, and these aren't necessarily going to be used today in our notes. However, they may come up in the future, and they are in this section of our text. So I just added them here. Make sure that you're just aware and highlight those for future use, that the limit as theta approaches 0 of sine theta over theta is 1, and the limit as theta approaches 0 of cosine theta minus 1 over theta is equal to 0. And both of these definitions are proved in your textbook if you wanted to take a look at the proofs for both of those. Example 1 asks us to find the equation of the line tangent to the curve at the given point. Our function is y equals e to the x cosine x, and the point is 0, 1. This is a problem that we've done many times before, trying to find the equation of a tangent line to a curve at a specific point. So we know in order to find the slope of our line, our first job is going to be to find the derivative of this function, because then if we plug the x value of our derivative in, we will be able to get our slope. So step 1, I'm going to say, is going to be for us to find our y prime. And our function that we're starting with is a product, e to the x times cosine x. So we know here that we're going to have to use the product rule when we do our differentiation. So my y prime is going to be equal to first d second plus second d first. First is e to the x, d second, derivative of cosine is negative sine x, plus second, which is cos x, d first, derivative of e to the x is e to the x. And then we can do a little simplifying because both of our terms have an e to the x. So just to make the math a little bit easier for ourselves in the next step, we can factor that e to the x out. And then I'm going to put the cosine x first and then minus the sine x second. That doesn't really matter, but it's just a little bit easier. Okay, so now we have an expression for the derivative. Y prime is equal to e to the x times cos x minus sine x. The second step in the process is going to be to find the slope. And our slope is going to be the value of the derivative at the point 0, 1. So my slope, m, is going to be equal to y prime of 0, which is equal to my derivative plugging in 0 for x. So e to the 0 times cos 0 minus sine 0. Slope is going to be equal to anything to the 0 power is 1, so e to the 0 is 1. And now we need to think about the unit circle. The cosine of 0 is 1, and the sine of 0 is 0. 1 minus 0 is 1, 1 times 1 is 1. So we get that the slope of our line is going to be 1. And then the third and final step in this problem is going to be to write the equation of the tangent line. Oops. And of course, to do that, we need to start with point slope form for an equation of a line. Point slope form being y minus y1 equals m times x minus x1. And we know our ordered pair is 0, 1, so it will be y minus 1. We know our slope is 1, and then it will be x minus 0. So now, if we clean this up, we get y equals 1x minus 0. Add 1 to both sides, and we get y equals 1x plus 1. Here is the equation of our tangent line of our curve at the point 0, 1. Example 2 asks us to find another equation of a tangent line, but then after we do the math, they want us to follow up by using our graphing device to sketch a graph of the curve and a graph of the tangent line on the same screen so that we can have a visual representation of the math that we just did. So for example 2, we're going to be doing the same things that we just did in example 1. We're going to begin by finding y prime, the equation for the derivative of y. And once again, I have a product here. I have a first and I have a second. My first function is 2x times my second function is sine x. So in step 1, when I find y prime, I'm going to be using the product rule. First d second plus second d first. So first is 2x. D second, the derivative of sine x is cosine x, plus second, that's my sine x, and d first is the derivative of 2x, which is 2. And then I can simplify this a little bit. It looks like I have a factor of 2 in common, so I can pull that 2 out, and then I have x cos x plus sine x. All right, now the second step in my process is going to be to find my slope. And I know that my slope is going to be equal to the derivative evaluated at the x value of my point. So I need to find y prime of pi over 2, which means I'm going to be plugging in pi over 2 for x. So now here's where I need my unit circle again. Hopefully you remember the ordered pair at pi over 2 is the top of the circle, and that ordered pair is 0, 1. So my slope is going to be equal to 2 times pi over 2 times the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. Well, pi over 2 times 0, that's 0. So I end up with 2 times 1, which gives me a slope of 2. So now I know that the slope of my tangent line is 2. The final step in my process is going to be to write the equation of the tangent line. And again, I am going to begin that process with point slope form. And it will be y minus pi is equal to my slope, which was 2 times x minus pi over 2. And when I solve for y, I get y equals 2x. 2 times negative pi over 2 is negative pi. And then when I add the pi over from the other side, I get a y-intercept of 0. So my tangent line is y equals 2x. Now I'm going to grab my graphing calculator and I'm going to graph both my function and my tangent line on the same screen. Okay, I'm in my y equals and I have cleared out what was there, so I'm ready to type in my two functions. My first function is 2x sine x. Close that parenthesis there, and then the second function is just 2x, my tangent line equation. One thing I want to point out, we are graphing trig, so we want to make sure that our calculator is in radian mode. If you are not in radian mode, if you're in degree mode, you need to change to radian mode. And then since I'm graphing trig, I am going to take a look at my window here because I want to use a window in terms of pi instead of in terms of 1 through 10. So I'm going to set my x minimum to be negative 2 pi. Pi is above the caret key. So negative 2 pi. I'm going to set my x maximum to be positive 2 pi. I will have my x scale count in increments of pi over 2. And I will do the same thing, or on my y's actually, since I have my ordered pair that my tangent line is at pi over 2 pi, I'm actually going to count, I'm going to do the exact same thing for my y min and my y max. I'm going to do negative 2 pi as my y min. I'm going to do positive 2 pi as my y max. And I am going to count my y scale in terms of pi, or excuse me, at pi over 2. All right. So now I'm ready to take a look at the graph. Okay, and as we can see, that 2x times sine x, that does some crazy things, right? But it still does look like, it still does look like, you know, some sort of a trig function. It's got the, you know, oscillations in it. And then there's my tangent line, and you can see that the equation of the tangent line here, or the tangent line itself, has an intersection point right here. All right, so now let's graph a picture of what this looks like in our notes. Doesn't have to be perfect. We're just looking for the general idea here. All right, so my first curve was my sine, and it kind of went off the graph down here. I know that it obviously comes and turns back around because it crossed here at negative pi. Then it came up, did something like this, went off the graph again, but then it came back up here like that, right? So that was our 2x sine x, and then our tangent line, y equals 2x, had its intersection point like right here. And it looked like that. Example 3 asks us, on what interval is f concave downward? So now we need to apply some previous knowledge. Let's go back to thinking about section 2.10 when we talked about what does f prime tell you about f. If we want to know when f is concave downward, first of all, there's two ways that we could do this. One way is the graphical method, I will call it. So let's write this down because I'm going to show you both ways. And for the graphical method, what we have to realize is that f of x is going to be concave down wherever f prime of x is decreasing. Let's write that down. F of x is concave down wherever f prime of x is decreasing. So in order to be able to answer this question, we need to look at a graph of f prime of x. Well, we know that f of x is 2x minus tangent x. So now we have to find f prime of x. And f prime of x would just be the derivative. The derivative of 2x is 2. And the derivative of tangent is secant squared. The negative comes along. So 2 minus secant squared x would be f prime. So if I look at the graph of 2 minus secant squared x on this interval right here, I should be able to see where the graph is decreasing, and that would be the answer to my question. So I'm going to sketch a quick coordinate plane here, and then I'm going to grab my graphing calculator, and I am going to graph what this looks like. I'm going to go ahead and clear out what I had already in my y equals. And I'm going to type in my function. Now, you may notice that we don't have a secant here, right? Remember that secant is the reciprocal of cosine. So when I type this in, I'm going to type in 2 minus, and then I'm going to use a parenthesis, and it's going to be 1 over cosine quantity squared. So 1 divided by cos x. I have to, whoops, too many x's there. 2 minus, parenthesis, 1 divided by cos x. So I need to close the parenthesis on the x, and I need to close the parenthesis on the 1 divided by cos x, and then I need to square that. So this would represent 2 minus secant squared x. And I can leave, I have my y window in there from the last problem. I can just leave it as it is. That's fine. And I'm going to take a look at the graph. But again, I'm only interested in what is happening between negative pi over 2 and positive pi over 2 on the x-axis. So now I'll go back to my window and I'll just change my x min to negative pi divided by 2, and I'm going to change my x max to positive pi divided by 2. And now let's take a look at the graph. Okay, so we can see that this function, if you look at the graph from left to right and see where my arrow is here, it is increasing from here to here where it reaches its maximum, and then it is decreasing from here to here, knowing that this goes, all the way down, that there is actually an asymptote here at pi over 2. Secant actually has an asymptote there. So the answer to my question then, where is f prime of x decreasing? It's going to be on the interval from 0 to positive pi over 2. So I'm going to go back to my notes. I'm going to sketch a little picture of what my function looked like. Kind of just looked like a parabola, like this. But keep in mind that secant has asymptotes. So we have an asymptote here, and we have an asymptote here. And this is pi over 2, and this is negative pi over 2. And so our function is decreasing along here. So we would say that the answer to our question, where is f of x concave down? F of x is concave down on the interval from 0 to pi over 2. And this is how we would solve this problem graphically. But I did mention that we could also look at this problem algebraically. And algebraically, we could say that f of x is concave down wherever f prime prime, so second derivative of x, or of f of x, is negative. So let's write that down. F of x is concave down wherever f prime prime of x is negative. Which means that I'm going to have to find my second derivative. So I start again with f of x. F of x is 2x minus tangent x. I already found f prime before, which was 2 minus secant squared x. So now I just have to find the derivative of this. Now keep in mind, 2 minus secant squared x is secant x quantity squared. So now I run into a problem, because if I have to find my second derivative, I have to be able to find the derivative of a trig function squared. Oh, shoot, I don't know how to do that yet. Okay, so f prime prime of x, I've run into a problem. This requires something called the chain rule. And since I don't know what the chain rule is yet, that is section 3.5, I'm going to have to wait on this, okay? But I want you to know that algebraically speaking, I could do this once I have a little bit more knowledge. All I would have to do is find the second derivative of the function, figure out what the critical values are, and then do sign testing to figure out between the interval of negative pi over 2 and pi over 2, which intervals are positive and which intervals are negative. And obviously I'd be looking for the negative intervals because that's where f of x would be concave down. But just so you know, you do get the same result. You end up with the interval from 0 to pi over 2 as being negative. And so by the algebraic method, you would get the same answer as you would get by the graphical method. I always like to show you multiple ways to do things in calculus, keeping in mind that when we get to the AP test in the spring, parts of the test are with a graphing calculator and parts of the test are without a calculator. So if you had access to a graphing calculator, I would totally have done the graphical method on this problem. But if this were the question on the AP test and you didn't have a calculator, then you'd have to do it the algebraic method and you'd have to be able to find the second derivative so that you could figure out where the second derivative is negative. So again, this is section 3.5, which is coming soon. Example 4 says, a mass on a spring vibrates horizontally on a smooth, level surface. Its equation of motion is 8 sine t, where t is in seconds and x is in centimeters. A says, find the velocity and acceleration at time t. B says, find the position, velocity, and acceleration of the mass at time t equals 2 pi over 3. In what direction is it moving at that time? Well, in order to do part B, we have to first do part A. So we are given the function that they're calling it x of t. I'm going to call it s of t just because we're used to our position functions being s. So s of t is equal to 8 times sine of t. And they want us to find the velocity and the acceleration. Well, we know that velocity would be equal to the derivative of position. So I just have to find the derivative of 8 sine t. Well, the coefficient 8 comes along for the ride, and the derivative of sine is cosine. So the function for velocity would be 8 cosine t. And then we know that acceleration is the velocity's derivative. So now I just have to find the derivative of 8 cosine t. Again, 8 comes along for the ride, and the derivative of cosine is negative sine. So I'm going to put the negative in front of the 8 and then sine t. Then part B asks us to find the position, velocity, and acceleration at t equals 2 pi over 3 seconds. So now this is easy to do. All I have to do is plug in 2 pi over 3 for t in each of my equations. So the position at 2 pi over 3 seconds is going to be equal to 8 times the sine of 2 pi over 3. The sine of 2 pi over 3, when you look at your unit circle, is square root of 3 over 2. So this is going to be 8 times the square root of 3 over 2. 8 divided by 2 is 4, so this simplifies to 4 square roots of 3. And if we're talking about position, then we know that our units here are going to be centimeters. And the question is, the second part of the question is, in what direction is it moving in at that time? Well, 4 square roots of 3 centimeters is a positive value, so we would say that it is moving forward at that time. My velocity at 2 pi over 3 seconds is equal to 8 times the cosine of 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2. So 8 times -1/2 is going to give us -4. And the units for velocity are position divided by time, so -4 centimeters per second. Since our velocity is negative, we know that at that point in time, it's moving backwards. And then finally, for velocity, and then, or it has a negative velocity, I guess you could say. And then finally, acceleration at 2 pi over 3 seconds is going to be -8 times the sine of 2 pi over 3, which is going to be -8 times the square root of 3 over 2, which gives me an acceleration of -4 square roots of 3. And the units on acceleration are centimeters per second squared. So again, I know that it's going to be moving backwards. Our final example, example 5, says to find the derivative by finding the first few derivatives and observing the pattern that occurs. So they want us to find the 30th derivative of cosine x, but they don't actually want us to do the derivative 30 times. Instead, they're suggesting that there's going to be a pattern that's going to occur, and we're supposed to discover what that pattern is. So we are beginning with the function y equals cosine x. So we know that the first derivative, dy dx, derivative of cosine is negative sine x. Okay, so this is the first derivative. Then we know that d squared y dx squared, that would be the second derivative. So the derivative of sine is cosine times the -1 means that the second derivative of cosine would be negative cosine x. And then my third derivative, so d cubed y dx cubed, is going to be the derivative of negative cosine. Well, the derivative of cosine is negative sine, so negative sine makes sine x. That's going to be my third derivative. And the fourth derivative is the derivative of sine x is cosine x. And that is what we started with. So basically, the fourth derivative is the same as the original function. Here's our original. Here's our fourth derivative. They are the same. The fourth derivative is the same as the original function. So that tells us that after every 4 derivatives, you are back to cosine x. After every 4 derivatives, you are back to cosine x. So we need the number closest to 30 that is divisible by 4. That number would be 28, right? That's the closest number to 30, less than 30, that is divisible by 4, right? Because 29 is not and 30 is not. But we know then that the 28th derivative, so d28 d28y dx28, the 28th derivative of y with respect to x, is going to be equal to the original function, which is cosine x. So then that means that the 29th derivative is going to be equal to negative sine x. And the 30th derivative is equal to negative cos x, right? So that answers our question. Using this process, you should be able to find any derivative of cosine. If I asked you to find the 257th derivative of cosine, you would figure out the closest number to 257 that is divisible by 4, and you'd start from there. So you'd at most have to find just a couple of derivatives.